Hello wonderful person, this is Anton, and today we're going to try to resolve the mystery of the oxygenation of planet Earth. Why does our planet have so much oxygen, and did something specific happen to planet Earth that resulted in the sudden increase in oxygen on the planet? With one recent paper suggesting that the answer could be yes. Something might have happened to planet Earth millions and millions of years ago, providing the necessary conditions for the sudden oxygenation of the entire planet, for the evolution of complex life, and for the evolution of intelligence on the planet as well. All of this was a result of oxygen. But what caused this oxygenation event? So that's the question we're going to try to answer today. Something that was recently discussed in this paper you can find in the description below. And let's start with the answer itself. Or I guess let me give you the spoiler. The scientists in this paper believe that it's actually the rotation of the planet, or the speed of the rotation, that caused the planet to suddenly have a lot of oxygen. But they give a really unique and extremely interesting reason for why they think so, and explain this using a very interesting example from planet Earth. But before we start with the explanation, well, you have to remember that Earth constantly changes its rotation speed, even though we don't generally notice it. For example, the tragic Indian Ocean earthquake event from 2004 changed the rotation of the planet by roughly around 3 milliseconds. It doesn't sound like a huge change, and it's not, but it's still there. Even certain human constructions change the rotation of the planet because of the distribution of mass that they cause. The Chinese Three Gorges Dam, for example, changed the water level so much that the calculations show it changed the rotation of the planet by 0.06 milliseconds. But these examples of rotation change are kind of trivial. Most of the rotational influence on the planet come from our own moon. The moon is responsible for the majority of changes when it comes to rotation speed on planet Earth. And so here, even though modern day is roughly around 24 hours in length, if our moon did not exist, if it wasn't actually orbiting planet Earth, even after 4.5 billion years of orbiting the sun, the day on Earth would be roughly around 6 hours long. And that's because the tidal interactions between the Earth and the Moon are directly affecting their sort of orbital dance around one another and also their rotational speed. And this is why the Moon is always facing Earth with the same side, because of these tidal interactions and because of the way that they actually influence one another. And the way the story goes is as follows. So about 4.5 billion years ago, a slightly smaller planet known as Theia very likely collided with early Earth. And today we refer to this as the giant impact hypothesis. And following the initial impact, the debris that's formed around the planet eventually formed the early moon. And so approximately 30,000 years after the collision, a single day on Earth was about 6 hours long. But within about 16 million years, because of the Earth-Moon interaction, this actually decreased to about 10 hours. And in case you were wondering why, well, the short explanation goes as follows. As the moon orbits the planet, it creates the lunar tides that you see right here. It's like these two protrusions on both sides of the planet. But because our planet is also spinning, and it actually spins faster than the orbit of the moon, the tidal bulges end up getting shifted just a little bit in front of the moon. And so the moon ends up pulling at these tidal bulges, which ends up slowing down the rotation of planet Earth. And it's going to keep doing this until the rotation of planet Earth matches the orbit of the moon. Or basically until planet Earth is facing the moon with the same side as well. This right here is referred to as the tidal braking. And this tidal interaction between the moon and Earth ends up doing two things. First, it obviously slows down the rotation of both objects, but it also ends up transferring some of the orbital energy away from the moon, which ends up moving the moon farther and farther away. And so even though initially the moon was really close to planet Earth, possibly about few tens of thousand kilometers away from the center, eventually it moved to the region where it is today, almost 400,000 kilometers away. But in the beginning, when the moon was really close to planet Earth, that's when it had a lot of effect on the rotation of the planet. It was much easier back then for the moon to slow down our planet. But as it moved farther and farther away, the effects dropped dramatically as well. And so it took about 1 billion years for the planet to have a day of about 12 hours, which also coincides with the first signs of life on the planet. But for about 1 billion years, the life stayed more or less primitive. This is actually before the photosynthesis, before the multicellular life, and before anything complex started to appear. But by the time the first photosynthetic life started to appear on the planet and the first oxygen started to be produced, a single day on Earth was roughly around 18 hours in length. This was approximately 2.5 billion years ago. And when the first multicellular life appeared, the day was already 23 hours long. And so the scientists in this recent study actually believe there is a very specific reason for this, and this is not just an interesting correlation. They do believe that the rotation of the planet served to sort of help life evolve and to produce more oxygen. And so here's how they reason about this and how they found some of the evidence. We know that pretty much most of the oxygen on the planet today is formed by photosynthetic life, which is actually one of the reasons why a lot of scientists today believe that by finding oxygen somewhere else out there, on another planet, we might be able to find some kind of extraterrestrial life as well. But what is unusual is that it took such a long time for the oxygen to actually become prominent on the planet, and it took several major oxygenation events for the life to become suddenly diverse and for the oxygen become everywhere. As a matter of fact, between the first signs of oxygen approximately 2.5 billion years ago and the appearance of a lot of complex life, there is a period of about 2 billion years that is kind of difficult to explain. In other words, why exactly did it take so long for the oxygen to become established on the planet? What factors could have played a role in establishing the oxygenation events and in making complex life possible on the planet? And in this particular paper, the scientists believe that there was really probably one main factor: the rotation speed of planet Earth. And so let's discuss the evidence, and it's actually from a place in North America, Lake Huron as a matter of fact, very close to the border of Canada. And in this case, I wanted to use Google Earth to show you exactly where they studied a lot of these formations that were discussed in this paper. So it's very close to the lake shore, near a place called Alpena that you see right here, and there are several islands here that seem to contain very unusual sinkholes that are quite easily visible in this map from Google Earth. These blue formations, these are sinkholes. There's one right here, there's another one right here, and there's actually quite a lot of them all over the place. And completely by accident, a lot of these sinkholes form these very unique and somewhat isolated biospheres that contain life that seems almost archaic, it seems almost ancient. There's practically nothing else that's surviving there because there is so little oxygen, but the bottom of these sinkholes contain something that looks like another world. It's these unusual mats of cyanobacteria, with some of these mats being purple in color because they contain a very specific type of a purple oxygen-producing cyanobacteria that's existed on the planet for approximately 2.5 billion years. Now in this particular paper, they focused on the sinkhole around this island right here that's known as the Middle Island. And specifically, it's this one here. And these sinkholes create extreme conditions. There's practically no oxygen on the bottom other than the oxygen produced by these unusual cyanobacteria. And because there's practically no other life present here, for example, no plants, no fish, almost nothing can exist here. Okay, some fish can exist, but not for a very long time. Because of this represents a kind of a picture of what ancient Earth might have actually looked like. Or actually what ancient Earth looked like for billions of years during the existence of these early cyanobacteria and early bacteria that were responsible for some of the early gases on the planet. Now it just so happens though that this is not the only organism living here, and as a matter of fact these purple cyanobacteria are sort of competing for space with the other bacteria, and specifically the white sulfur oxidizing bacteria that instead of oxygen actually use sulfur. And so while the cyanobacteria need oxygen to generate energy, the sulfur-loving bacteria need sulfur. But they both live in the same space and they both compete for the space. So for example, once in a while, a gas from inside the planet, like methane or hydrogen sulfide, will create these unusual bubbles that you see right here. And these finger-like formations are used by the sulfur-loving bacteria to essentially live and to produce energy. Generally, during nighttime, or essentially from dusk until dawn, the entire upper layer is dominated by the sulfur-loving bacteria, with the cyanobacteria being underneath, so essentially, if you were to shine a light here, it would all look more or less white. Mostly because the sulfur-loving bacteria are white in color. But then the sun comes out, and the cyanobacteria start to come up to the top, pushing the sulfur bacteria underneath them, and they stay this way for the entire day. And turns out they do this kind of a dance every single day. When the sun is out, the purple is on top, when the sun is down, the purple is in the bottom. I guess kinda makes sense. But what the scientists recently realized is that, well, it seems that there is a slight delay. Every single day it takes at least a few hours for the cyanobacteria to sort of dominate the top, to actually come up to the top, to start producing all of the oxygen and to start producing all of the energy they need. In other words, it's not an instant event. There is a slight delay in their response, and because of this, they are only limited to a few hours per day to be able to produce the oxygen and of course to produce all of the energy. And this gave the scientists a kind of a hint. Well, what if the Earth day was much shorter? Would they actually have any chance to produce any oxygen whatsoever? And so to try to investigate what kind of results they would get, they crunched the numbers using global models for oxygen levels. With this figure right here sort of showing their discovery. With a day that's only about 12 hours long, practically no oxygen is created at all. When a day was about 16 hours long, you get a little bit of oxygen, and it's really only when the day is about 21 to 24 hours long where you suddenly start getting quite a lot of oxygen released by the cyanobacteria that does tend to take its sweet time to start producing oxygen. With a day that's about 52 hours long producing pretty much double the amount of oxygen we have today. And if we compare what we have in this graph to what we know about the planet Earth historically, so this right here corresponds to the creation of early life on the planet 3.5 billion years ago. Whereas this right here corresponds to some of the early life that produced oxygen, and this right here is closer to the Great Oxygenation event. More importantly, because we know that there was also an oxygenation event approximately 800 million years ago, this study and the results from the study would actually explain why it happened. The Earth slowed down even more, allowing more cyanobacteria to produce even more oxygen. And so overall, this is a really brilliant discovery. It sort of combines the physical observations from the activity of the Moon and Earth and the tidal effects, and links it all together to the creation of life and complex life on the planet, and to the creation of oxygen on the planet as well. Altogether implying that the rotation of the planet is extremely important for the production of oxygen. The slower the rotation, the more oxygen you can expect. Or at least that's what it seems like. I'm sure some of the further studies might actually clarify this even more. But right now what this implies is that, well, when we're looking for some exoplanets out there, if they're spinning too fast, they might have a very similar problem. Any kind of a complex life present on those distant planets might just not get enough time to produce the energy it needs if the rotation of the planet is too quick. And so even though the phosphorus-loving or any other chemical-loving bacteria might be just fine, if the bacteria or cyanobacteria require sunlight, they might have trouble depending on how fast the planet is spinning. And so definitely a really cool discovery from this lake right here on the border of Canada. But for now, that's kind of all I wanted to mention. I'm sure there's going to be a lot more to follow and a lot more follow-ups with more explanations. For now, that's all I have for you. Subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Maybe support this channel on Patreon by joining the channel membership or by buying the Wonderful Person t-shirt you can find in the description. Either way, stay wonderful, I'll see you tomorrow, and as always, bye bye.